few sort of specific examples, but this, I'm just going to set myself a timer because I'm really bad at keeping time. There we go. Okay. The MUI library, the Multiscale Universal Interface, is an integral part of the CCP-WSI software work plan and also the HEC-WSI software work plan. So that's sort of one of the reasons for the link, I guess, in bringing it to this meeting. But as a library, it was actually originally designed specifically to couple particle type methods together. So actually SPH with dissipative particle dynamics. It's grown very significantly since that point. I'm going to sort of give a general overview of the library, but the intention of this talk really is hopefully to give people an insight into how it might be able to be introduced into workflows where you're using particle methods, possibly ethically. So I think the very first thing I wanted to do, because the SPH community really has embraced coupling and code coupling as an idea, multiphysics and all those sorts of things, but in a very specific way. And so what I've seen a lot with the SPH community is the idea that everything should be solved using particle-based methods. And I've seen that a number of times. And I guess what I want to do first is to give you some context as to why I think perhaps we should think of SPH as one of a toolkit. In the multiphysics world, one of a toolkit of solvers that we should all sort of try and work into coupled solutions. So taking an example that's pertinent for CCP-WSI, so a floating offshore wind turbine. So this is one of the key use cases that community uses to drive things forward. So if we consider this, and also just to say, this use case is part of the CCP-WSI data repository set. So one of the really great things the CCP does is this idea of creating this online data repository and data set. So if you go to, these slides should be shared for those online, but if you go to this link on the CCP-WSI website, you'll find a complete and interesting data set able to be used to reproduce aspects of the floating offshore wind turbine case. And there's lots of other examples of things that have been produced at various facilities at Plymouth and other places like that. So really, really well worth having a look. But anyway, so if we look at the floating offshore wind turbine problem and ask ourselves, well, we can't because Zoom's put a bar over it, but why do we want to do coupling? So the question really is, how do we break this down? And if we think of a problem like this, then I am going to read the screen because there's quite a lot here, but we have rigid floated body dynamics in the near field to the object. We have multi-phase fluid dynamics and single-phase aerodynamics, perhaps. We have the seabed to consider, so maybe soil dynamics. We have the anchors, so soil structure dynamics. We have a flexible tethering to consider. We have the far field, so where we have potential flow, and we have potential flow for the fluid dynamics, aerodynamics. We have maybe atmospheric modeling to consider, and then maybe flexible structural mechanics for the turbine itself. And so when you look at this as a problem and think, could I use one code to solve this? I'm hoping everybody's kind of thinking, well, actually, no, there's probably multiple solutions to the various aspects of this problem that we need to use. So it's complex multiphysics or potentially multi-scale problems. And just to define what I mean by multi-scale, this is problems where the length or time scales involved in the two things that you're coupling together are significantly different, orders of magnitude different. So often we might refer to things like molecular dynamics type simulations coupled with CFD type simulations and those sorts of things. So rather than it being millimeter to meter, it would be millimeter to maybe kilometer, but it's be more or less those sorts of things. It's a bit nondescript, but. So the question, can't the floating offshore wind turbine problem be solved just using particle-based approaches? So I've seen a number of really good examples of full frameworks, software frameworks, where people have just used particle methods and they've used it for various different things. We all know that you can actually do solid mechanics, you can do fluid dynamics and all those sorts of things using the SPH method alone. So shouldn't we just solve this all using the same particle approach? So a monolithic methodological approach is often possible to a point. But we have to ask ourselves the question, is it sensible? And the other aspect is a monolithic software approach. So when we talk about coupling, we often talk in terms of loose and tight and monolithic and partitioned. So by monolithic, we mean a solution that's all in one place. And you can look at this algorithmically, and you can look at this in terms of the software. So if you have a software approach where you have multiple solutions, but all in the same executable, in effect, it's feasible, but again, is it sensible? So my personal opinion is actually almost always taking a partitioned approach to code coupling is the best and most sustainable approach. It's not always the most mathematically rigorous. It's not always the most conservative approach. Sometimes there are better approaches than that. And obviously it's down to the scale of the problem and what you're coupling to what and for what, as to whether or not you think it's worth going down this route. But it's usually the most sustainable. And by that, I mean, if you have a simple FSI problem, for example, fluid structure interaction problem, where you need a structural solver, you need a fluid solver, and you have a really good structural solver that's developed by a big team of people that do really good work and have been working on it for a decade, and you've got a really good fluid solver, the same. If you join those two codes together into a solution, you get the benefits of both of those teams' development of their maintenance and all their skill sets. Whereas if you try and integrate the structural solution into the fluid solver, for example, the people doing the fluid solver have to be the ones to maintain all of that. And so and when you consider the floating offshore wind thing we've just seen and all of the potential sort of physics needed, that problem just grows and is exacerbated. So from a sustainability perspective, that's one of the key drivers for me. So particle methods for some aspects, mesh-based approaches for others. And I guess that's the interesting thing. So, okay, so with that context, I want to move on to the Multiscale Universal Interface. So in true BBC style, it is one of a number of coupling libraries out there. There are other coupling libraries available. They all have different sort of strengths and weaknesses. I would go as far as to say, though, that MUI, the Multiscale Universal Interface that I'm presenting here today, is the only one that uses a particle paradigm as its data structure. The rest all tend to use some sort of mesh-based structure underneath. And that's one of the reasons I think it's particularly well suited to coupling SPH with other things and other particle methods with other things. So I won't go into any detail of the other methods and the other libraries. I have good working relationships with a lot of them. So if you'd like to ask me any questions, please do. But MUI itself is a whistle-stop sort of tour of the software. It's written in C++ in the C++11 standard. There are wrappers for C, Fortran, Python. It's open source. So it's licensed with 2 different licensing structures for anybody who's interested in these things. But one of them, Apache 2.0, is very permissible. So you can almost do what you want with it. It's a header-only design. And that's a really important difference. So its only external dependency is MPI. There are no other library dependencies at all. So you integrate MUI into your code. It creates a peer-to-peer MPI interface between 2 or more codes. And there are lots of things there. There's a website, there's the library itself. It's all on GitHub. There's a demo repository and a big benchmarking framework. So I don't want to hang up. No. So if we want to do multiphysics or scale coupling using MUI, in effect, MUI provides a toolkit for us to do that. And that's the best way of looking at it. So it allows us to create couplings between mesh-to-mesh methods, mesh-to-particle methods, and everything else in between. And it offers the ability to couple across both length and timescales, as the name suggests. In actual fact, the majority of our use cases are what I would refer to as multi-physics. So despite it being called the Multiscale Universal Interface, it's applicable, it's all about being able to couple together codes, transfer data between them. So where you have reasonable length scales in a multi-scale problem, that can be tackled through the various sort of aspects of this toolkit that I'll show you in a second. Where you have reasonable timescales, that can be considered as well. However, at the point where direct multi-scale coupling is no longer feasible, so in the example of connecting molecular dynamics to CFD, for example, there's a lot that happens in between the molecular sort of nature of MD and macroscopic CFD, and just saying I'm going to couple MD to CFD actually makes very little sense in most scenarios. You need to do something with that. You need to parameterize your CFD simulation with the output of the MD or something like that. So at that point, MUI can still be used purely for a tagged data transport framework. So it can still be used to create a coupling, but you might not do necessarily sort of direct interpolation type things between the codes. And this is about as technical as I'm going to get in terms of the computational science side of things. So it uses the MPI multi-program, multi-data paradigm. So this is a well-defined part of the MPI standard. There are lots of different ways that an MUI could connect codes together, but it uses MPMD. Most coupling libraries do, bar one. But what that does, it allows large numbers of applications to be coupled together simultaneously. So, okay, so as an overview then. So in effect, it couples using a set of discrete data samples and an interface. So we take domain-specific representations and we convert them into a general form, in this case, points. So a cloud of points, and each of the points in the cloud has associated data. For anybody in the room who uses SPH, it might be sounding similar. So if we have our finite difference element or molecular dynamics problems, as you can imagine, you can generalize this into a cloud of points. So if we take an example where we have two solvers, so this might be an example of a one-way coupling. So solver A, application A in this diagram, imparts data at a point. So the point might be anywhere sensible within its own domain-specific representation. So it might be at a face center if it's a mesh-based. It might be at a node location if it's a finite element, so on and so forth. With an associated timestamp data frame using non-blocking operations. That's quite an important thing. So MUI is a non-blocking send, blocking fetch library, and that's how it allows you to create a synchronized coupled simulation. So this cloud of points can be very, very large and has a data frame sort of encapsulating it. So there's a timestamp associated with each of these clouds. And then on the other side, application B in this diagram requests data at a specific location and time from the interface using spatial and, if you want, temporal samplers. And this is a blocking fetch operation. And in a nutshell, this is a coupling sort of workflow using MUI. So I'll go into a bit of detail in a second about the spatial and temporal samplers that are in the library, but generally speaking, this is kind of how you would couple two codes together. So in terms of what's in the toolkit, there's an application programming interface to create an MPI-based interface between two or more applications. There is a limit to the number, but it's in the MPI standard rather than a limitation with an MUI, and it's a very large number of processes that you can couple together. It's an extensible, so an extendable or something that you can add to it yourself, framework of spatial and temporal samplers, as well as a collection of what we've termed coupling helpers. So as you download it, it provides 10 spatial samplers, so a simple Gaussian, a quintic SPH approach, and a full radial basis function approach with both conservative and consistent modes, as well as I think many others, 7 others, I've given it a number. There are also temporal samplers allowing simple concepts, so summation, averaging in time, but the scope of the temporal framework is far greater. You could do a lot more with this, it's just we haven't really yet. And also then you have the idea of the coupling helpers. So these basically provide functions to enable common coupling approaches. So for anybody involved in fluid structure interaction, you're probably aware of the Atkins method, for example. It's one of the typical tight iterative coupling approaches used in FSI. So there's a helper function to enable you to create an Atkins approach in your code. Again, this is extensible, so you can add different helps. It also provides a full custom linear algebra solution for both dense and sparse problems. It's not a big solution, it's a minimally viable solution for what we need it to do. But that's currently used within RBF, and this is why it has no external dependencies on other libraries like Eigen or PETS. Okay, so it would be remiss, given we've just talked about HEC-WSI, for me not to just say this is actually a high-performance solution. This is something intended to be used on big HPC systems. And so we've recently done some testing of this library just to see how well it scales and how well it works on big systems. So I won't go into too much detail, but basically this is an artificial benchmark that we did on the Archer 2 system of MUI. So MUI has its own artificial benchmarking tool, the MUI testing tool. And it allows you to create sort of an arbitrary coupling scenario and then scale it up to very, very large numbers of cores. So in this particular example, this is a sort of simulated local computational load, and it assumes two CFD solvers that both scale linearly, and that's a really important thing. Most CFD solvers don't scale linearly, especially for problems involving a billion cells. However, for the the purpose of doing this benchmarking, that's the assumption here. So we're transferring 1 billion points between two instances, so 2 billions in total. So this might be an example of an extreme full volumetric coupling. And that's a total of 48 gigs of data transferred. So it's a big problem. And we're looking with and without, in this case, a simple Gaussian interpolation applied at each of the points, just to show sort of how the scaling is affected by introducing some computation through the library. And those are the results. So I don't know how well everybody can see them, but in effect, the line is the important one. So we're going up to about 102,400 cores. From memory, it's about 500 nodes, I can't remember. Whatever that is divided by 128. So nowhere near the entirety of Arch2. Arch2 has over 5,000 nodes. It's a big system. However, you can see the red line is what we would hope if we were getting absolute perfect scaling on Arch2 with this problem. And then the green and the blue lines are what happens if we do it with and without some sort of data interpolation at a point. So it's actually pretty good. We're actually just showing the Arch2 interconnect fabric works really very well here. We're showing that actually its communication ability between lots of nodes is good. But what we're also showing is that the library doesn't introduce any significant overheads that would stop scaling in your code. So if you have a code that scales to this level and you want to couple it to another code that scales to this level in Arch2, and you use MUI, MUI won't be a bottleneck in that. So what are we working on right now? So we're currently porting the linear algebra portion of the library to a heterogeneous programming model called SYCL. Others are available. And this is work that we're doing through an EKS Excalibur project and also through an Intel Center of Excellence, which we have where I work. And what this will do is it will enable cross-vendor GPU acceleration of the linear algebra solution. And initially that's used in the RBF spatial filter, but this is generally available throughout the library. So if, for example, you were to introduce your own spatial interpolation method into the library, you could call the linear algebra functions, and then working on the assumption that we've managed to do a good job, you could accelerate that on Intel GPUs, AMD GPUs, NVIDIA GPUs. We're also integrating the matrix data type. So we've actually only recently added this linear algebra capability. We used to have a dependency on a library called Eigen, which we wanted to remove. So we're actually integrating the matrix data types defined within our new solution so they can be used generally through the interface. So what that basically means is if you're using our library at the moment, if you want to send a matrix from one problem to another, you break that down and you send it individually and you rebuild it on the other side. This will allow you to send a complete matrix data structure through the interface. And finally, we're considering how to integrate data science, so AI, machine learning type things as an extensible framework, another extensible framework. And this really is quite feasible. Quite an interesting thing we might be able to do. So you're basically able to apply these sorts of methods directly as part of your coupled workflow, and MUI will be able to work on its own data at the point where it sort of has the data in its own searchable structure. Okay, so last two slides. I just wanted to show a couple of examples. I've tried to, we have a number of examples that I could have shown, but I've tried to pick out two that show the coupling of particle type approaches. So the first one is something that was done as part of an EU project that's just finished called SLOWD, or Sloshing Wing Dynamics. And this particular piece of work was done in conjunction with colleagues at CNR in Italy. Some really great work was done by Tom Rendell and Joe. I'm pointing to people that nobody on the cameras can see, but they are in the room, on other aspects of using SPH within this project. However, this was one piece of work within the project that specifically did use MUI. In effect, what was happening was a commercial CFD code, in this case, a code called SPH Flow, was being coupled with a commercial finite element solver called MSC Nastran. If you haven't used it, don't. If you have, best of luck to you. For sloshing problems. So this is a commercial SPH solver. It's a commercial finite element solver. It's very capable. If there's anybody from MSC listening, it's very capable. It's just not the nicest thing to work with. And in this case, we used MUI to transfer data and to synchronize the coupling steps between the two codes. So this is an interesting example because often when we talk about fluid structure interaction, most of the time we talk about iterative tight coupling algorithms because we're talking about coupling a volume of fluid code, for example, to a finite element solver. So this is an example of coupling an explicit SPH code to an implicit finite element solution. And so the conventional sequential staggered, I think I might have missed the word sequential out there, but the conventional staggered coupling scheme that's quite well known and quite well documented as working reasonably well in this scenario was used. So there was nothing particularly groundbreaking about the implementation that was done, except for the fact this was done to two commercial codes rather than it being two open source codes that played together easily. This was two commercial codes that really didn't want to talk. So we managed to make it work. And yeah, so some nice results were produced. So on the left-hand side, you can see, you've got left-hand side? On that hand side, you can see an example of a quite classic fluid structure interaction problem. So this is a rolling tank with a flexible beam in the center. And the results that were achieved were comparable with the literature using this. And on the right-hand side, that other side, you can see the actual ultimate goal of this within this project. So this was actually looking at a complex sloshing problem in a compartmentalized wing equivalent. I believe it's somewhere here on this university campus still, Tom? Yeah? That sounds like a great idea. It's a great idea. Yeah, so some really great work was done with that. But the sort of takeaway was it was actually relatively simple to do. Once you have the algorithm defined and the codes able to talk to each other, using MUI to sort of enable that was simple. So slightly different. So this actually isn't an example of a multi-scale modeling problem, believe it or not, despite the fact it's molecular modeling of gas dynamics, and it's coupling together two methods, molecular dynamics and another called direct simulation Monte Carlo. It's not multi-scale because both of the codes in this coupled solution are used at the same scale. It's just the scale is very small. However, it wouldn't take much to extend this actually to become a proper multi-scale solution. And that's because the direct simulation Monte Carlo method in itself is a multi-scale solution. And it's quite a unique approach, actually. If you're ever interested in simulating anything to do with rarefied gas dynamics, it's quite interesting. But in effect, what we were looking to do was to simulate the effect of evaporation. And if you do it properly, rather than doing it through a parameterized macroscopic CFD approach, there's a number of elements you need to consider. So there's an interface between where the bulk liquid and the bulk vapor exists. And then there's also something called the Knudsen layer between this interface and the vapor. And DSMC can be used to simulate the Knudsen layer, and then MD can be used to simulate the interface. And so effectively what we're proposing here is the need to couple CFD, macroscopic CFD with MD, MD to DSMC, and then DSMC back to macroscopic CFD to capture the entire thing. We never got as far as doing the macroscopic bits, but we did couple together MD and DSMC at the interface. So I won't go into the detail of the algorithm, partly because I'm out of time. But what that allowed us to do was to couple MD with DSMC. And then if anybody's ever seen anything to do with molecular dynamics, you'll be aware of the standard test that's used in the MD community. So it is a canonical ensemble. So basically we would expect this at a steady state to have a constant velocity and temperature, in effect, a constant energy. So we're looking for a flat line here. And it's just an open periodic thing where the molecules are allowed to do their thing, and you expect them to rest at an energy level. And if they don't, something's wrong with the MD itself. So something's wrong with the force fields, for example, and so on and so forth. And so what you can see on that wiggly graph at the top is the blue and the red show the energy in the DSMC and MD domains respectively. And then the green line is almost flat, and that's the coupled overall solution. So we're showing basically we're able to take two very dissimilar methods in some ways. One's a stochastic Monte Carlo approach, and the other is a full direct simulation MD. And couple them together to get a good answer. There were also some implications in terms of computational time. So this was just kind of showing the benefits of doing this, but I won't go into that. Okay, so in conclusion, MUI is a general purpose coupling library, and it's a particle-based approach at its core. So we've made it work with mesh-based methods, and we've introduced things like the radial basis function spatial filter to make it appropriate for use with mesh-based approaches, but actually it's directly appropriate for use with SPH. So you might introduce an SPH kernel in its spatial interpolation framework. You might do all of that within your own code and simply use MUI to push data directly without any interpolation at all, but it can be used directly with an SPH code. It can be used for both multiphysics and multiscale problems. It's suited for creating coupled approaches between methods and different discretization methods and time-stepping methods, and it's under active development. Any questions? Thank you.
Thank you, Stephen. So, yeah, any questions for Stephen? So, on the spatial coupling and interpolation, of course, there's implications for numerical accuracy there when you're coupling two different schemas.
Yep.
And as you said at the start, the mathematical analysis for coupling different methods generally is almost non-existent.
Yeah.
So, is there any guidance or advice we perhaps give on which interpreter is best for which scheme? So, for example, you can imagine say it goes for Bruce Green for finite elements to radial basis function, but there's some different interpreter is better for finite differences or SPH. So, is there some guidance that nothing will be
general guidance? Offers? Yeah, it's a really good question. I'm hesitant to say no. But in the software, no, there isn't. So some coupling libraries go down the route of providing complete coupled environments. MUI kind of takes a down the middle kind of approach. So it's really intended as a toolkit. So what I would hope is people would share best practice. Yeah. So so the development of the RBF method, for example, was driven in a large part by our involvement with Tom through the slowed network. So we already had that in there ever so slightly, but we've added so much more to it based on his feedback and guidance. I think if you were coupling SPH to, for example, dissipative particle dynamics, so I should say as well, it was smooth dissipative particle dynamics. So they're actually quite distinct methods. DPD is more fundamental. It works in the same way as MD in some ways. You define force fields and kind of hope you get the right answer. Smooth dissipative particle dynamics you can parameterize. So it's kind of the other way around. It's almost a hybrid between SPH and DPD. So in the case of coupling SPH to SDPD, those two methods have well-defined interpolation. And so if you have a boundary condition in your SPH code and you know how you're going to treat that boundary condition, there's a reason you're doing that. So you would use that, and you could integrate that into MUI, or you could simply do that in your code and use MUI as a way to transfer the data that you get at the boundary. The bigger question for me is whether you're going to do a boundary-based coupling or a volumetric coupling, so where you have an overlapping region. So in most cases of a particle-to-particle coupling, you need some sort of overlapping region. Very rarely does it work well if you have a boundary. Whereas typically, people talk about FSI and they talk about mesh-based approaches, they talk about boundary-based coupling. So if you look at the precise coupling library, for example, it was originally designed to enable boundary-based couplings, and it's a mesh-based approach. So they create a chimera mesh, effectively, in a sense. So I think that's probably the main thing. It's more about whether or not it's a volumetric overlapping thing or a boundary thing. And the nice thing about the particle approach is it makes no difference, really. the framework supports it. We don't need to worry about how do we create some sort of mesh in the sensors if you overlap them and those sorts of things.
I mean, is there sort of community of practice when MUI has? You can go on say a wiki of guidance
not in the way I'd like, and I think that's one of the challenges is how do we build up that community. It's one of those. It's the age-old problem. You put software out there, and then you track who uses it. And, people, generally speaking, I find at least, don't tend to build up communities, spontaneous community repositories of these things. They do their work, they publish the paper, and it's very good, it's very interesting. But then it's up to the library developers to gather all of that, to put it into one place, and we do our best. So we've got a section on the website of examples of a couple solutions that we've done that we're aware of. But it's tough. It's a challenging one to do.
We could, maybe in the future, though.
I mean, I would hope communities like this and CCP-WSI and those sorts of efforts can be part of that. But I think it needs a critical mass of use of the library first, which is why I'm stood there telling people about it.
Yeah, no, great. Yeah.
I'm just wondering why we use this for the.
Well. I don't necessarily. That was an example.
Because it has non-dynamic laws and the law in for. I'm just wondering, do you have any problem if I use this?
So the intent of this was to kind of talk about coupling of ideally particle methods to either mesh or other particle methods generally. In the examples that I showed, we were using. So in the example of Nastran, it was an implicit solution, partly enforced by the solver that we had to use. So maybe it would have been better to use a different solution. Maybe there were other approaches to use. From a general coupling perspective, it's all about the algorithm. You need to couple them together. So the classical FSI type iterative approach does assume use of an implicit structural and implicit fluid solver. That's why you iterate around in a time period. I don't have a specific answer to your question because the answer is all of those things can be enabled with MUI. Sounds right. If you're coupling SPH to an explicit FE code, then my guess would be the algorithm would be simpler, and you need to use some sort of staggered scheme.
Are there any questions online? I noticed there's a chat message.
Oh, there is a chat message.
Yes, but the best I can stick to the comment about an example of coupling of a very well-known and very efficient SPH open source code with other solvers will be very nice too. So it's by Expressflow and it's to the comment.
Yeah. Agreed. Yeah, I agree. Yeah. So it's worth saying. So I imagine if anybody's here is aware of the Joules physics code, that there's a very significant multi-physics capability to that code already. So they've introduced Mordin, the Chrono library, and all these things. But that's an example of a monolithic software solution. And in some ways, that's driven by the libraries that have been used there. So Chrono and Mordin both provide an API in their compiled library. And the idea is you embed them into your host code. And in the case of those two libraries, using them in a partition solution is difficult because they're not a standalone application. They're intended to be used as a library. So if you wanted to have a partitioned implementation of Chrono coupled to Joules physics or any other SPA solver, you'd have to first build a solver around it. And so it's not always clear cut as to the best way forward. And I can absolutely see why you would include Mordin and Chrono into Joules physics that way. But I guess my hope with them would be take something like Joules physics or any other SPH code, and you would then couple it to perhaps an open source and widely capable FE solver, for example, to enable FSI. So we are actually developing and maintaining something we call Parasif as well. I didn't mention that. So the Parallel Partition Multi-Physics Framework is another bad acronym. Sorry, Wendy, if you're online, it is a bad acronym. They're all bad acronyms, aren't they? So that's intended to be a collection of solvers. So at the moment, it's open foam and various sort of solvers built within open foam coupled to a structural mechanics solver that we've created from a framework called Phoenix. If anybody's heard of Phoenix, it's quite a well-known general purpose finite element solution. And we've used MUI obviously to create a relatively capable FSI solution, but I'm very hopeful we can incorporate Joule's physics directly into that.
There's a question by Chena Kesava. He asks, what kind of coupling algorithms are available for FSI problems? For example, quasi.
Yeah, okay. So this is sort of referring to the coupling helper framework, I guess. At the moment, it really is, so it's something we did quite recently through CCP-WSI, actually, the development that was made clear that we needed to do. So at the moment, there is fixed relaxation and an Atkins approach in there. However, it is really genuinely sensible. So I think next on our list, we use the quasi-Newton approach. But if there's any others, and they don't have to be sort of that kind of ilk, you know, so these could be staggered approaches. If you're able to generalize functions that can help to implement a staggered approach using MUI, you could add this into the coupling helper scheme, and I'm hopeful we'll be able to do that over time. But of course, it's an open code, and so user contributions are always welcome.
Okay, any final questions for Stephen from the room?
So the example showed that's suitable, I guess, for the evaporation cycle.
Yeah, maybe. Yeah. So I mean, at the moment, so actually we're doing some other work where we've actually quite successfully coupled DSMC to CFD. We're currently actually adding that into the Parasiv. So that will be with an open foam solver and a well-known DSMC solver called Sparta, which is developed by NASA. Developed by one person at NASA. It sounds very grand, developed by NASA, but the originator of the method also developed this code. It's just a very good code. So we intend to incorporate that into Parasiv soon. However, there's still the missing element of the coupling algorithm we currently have being able to support DSMC at anything other than it being treated as a single molecular level. So the method's able to scale. So you have your particles and parcels, as it often gets referred to in that community, and the parcel can be representative of millions of molecules, or it can be representative of one. It's an unbelievably scalable method for its specific use case. And at the moment, the method we have only really supports when you consider one parcel to equal to one molecule. It's not actually a huge extension. It's something that's on the list. It's been on the list for years. Yeah, the more difficult thing is how do you couple MD to CFD? DSMC to CFD is actually, it's fairly obvious how you do it.